So next up is David Schmenk, who's going to talk to us about RGB to DGR image conversion. Before we get to that, though, I just want to take a second and announce the two winners of the Blue Scuzzies. The first one was Josh Clark, and he chose a DB25, so I'll be mailing that out shortly. And the second one was Brian Weiser, and he's going to inventory his hardware and see which version he needs, either the internal or the DB25. So congratulations, folks. And next up is David to talk about the RGB to DHGR. Plasma is about ready to get a very big update. Many new features, but probably the most exciting is the double high-res graphics library. One of the tools for DHGR is an RGB image converter using a brand new technique to create images that would have been thought impossible back in the day. So Dave's going to talk to us about that, and let's roll the video.
This presentation is the spiritual precursor to my KFest 2017 presentation on NTSC Artifact Colors, the next generation, with the Apple IIGS's super high-res graphics mode. This presentation is using the Apple IIe and IIc's double high-res graphics mode with the Plasma double high-res graphics toolkit in the Pleiades environment. Feel free to ask questions on the Discord server, and I'll get to them after part 1. Okay, so the joke here is that the double high-res graphics mode memory map is so difficult to work with, only someone as cool as Darth Vader could have come up with it. We're looking at a screen capture of the Apple Win emulator using its color TV output. Take note of the colors and resolution of the DHGR image. For comparison, here is the output from an actual color CRT. Modern video solutions have gotten exciting with the HDMI adapters capable of NTSC artifacting. Here is my Apple IIc Plus with the A2C DVI adapter on a very cheap monitor with horrible black levels. When we switch the emulated output to an RGB card, notice how the colors and resolution are affected. As you can see, this technique works best on real and emulated composite color output. I'll be using Rob Sheehan's presentation program for my slides. Links to all software, videos, and disk images can be found on the Discord server. This presentation is all about creating a slideshow of pictures converted for display on a 128K Apple IIe or IIc using a new and unique algorithm. The first step in conversion uses an image editor, such as the GIMP, to prepare the image. Here I found an image of our hero from a speaker profile website to use as our test subject. We need to ensure the image is an 8-bit per channel RGB image before cropping it to a 4:3 aspect ratio. Cropping an image doesn't have to be perfect. Just make sure you keep the subject matter large enough so the details don't get lost in translation. Once the image has been cropped, it has to be rescaled to the resolution of the double high-res graphics screen, 560 by 192 pixels. You need to break the link between the horizontal and vertical scales because this definitely is not a one-to-one scaling. Finally, the image has to be exported as a portable network image format using an extension of .pnm. Make sure it is exported using the RAW format. The first conversion option is to import the PNM file to the Apple II. Here I am using Apple Commander to import the test image into the 32 megabyte Pleiades Disk Images DHGR Toolkit Utilities directory. Booting the Pleiades disk image in an emulator, or preferably accelerated Apple II, change the directory prefix to the DHGR Toolkit's utility. Let's look at some pre-converted images in the samples directory. We can convert the Darth Vader image from the intro. If you are running in an emulator, now is the time to max out the emulated speed. The converter displays the results in real time as it reads the RGB pixels and displays the double high-res graphics image. To end the conversion prematurely, press Ctrl-C. Run the converter without parameters to see a list of options. Some of the earlier samples were in a more simple format with a .rgb extension. To convert these image files, use the -R option. Include a second destination file name to save the resulting double high-res graphics image into. Here I save the test.pnm image into the test.dhgr file. Under most circumstances, the default options will create an acceptable result. What do you think? The other conversion option is to use the command line interface on a modern operating system. For Windows, download the executable file and run it just as the Plasma version in a command window. For Mac OS, Linux, or Unix, download the converter C source code and compile it before running it. Again, run the converter just like the Plasma version. You can optionally compress the resulting image file using the LZ4 compressor, but I don't actually recommend this. You then need to import the DHGR image file into your disk image. At this point, we're ready to run the slideshow on some pre-converted images. For starters, we can run the slideshow on compressed images and see why I don't recommend it unless space constrained. Under the DHGR Toolkit Utilities directory is a slides directory containing some compressed images with the LZ4 extension. We can run the slideshow telling it to decompress all the files ending in LZ4. The decompression operation leaves an annoying pause halfway through displaying the image. Image quality isn't affected except in certain cases. But again, this is a feature I don't recommend. Press Ctrl-C to exit out of the slideshow. Here we will run the slideshow on regular double high-res graphics images ending in DHGR. Notice how much better it looks. The default is to pause 4 seconds between images. This can be overridden with a command line option. Press space to immediately advance to the next frame and Ctrl-C to exit. If there is only one slide to display, it will stay on the screen until any key is pressed. The converter has a rudimentary gamma adjustment Useful for final tweaks to the lowlights. The values range from 2 to -2 in integer increments, 2 being the darkest and -2 being the lightest. 0 is the default. It is better to adjust the light levels during the initial image manipulation in the GIMP. I've pre-converted the test image using a range of gamma values and displayed them in a slideshow so you can see the effect of the gamma. The NTSC conversion algorithm calculates the subcycle colors every time it's run. This allows a tint adjustment to be easily done. The values is in degrees and usually between -22 and 22, but large values can also be used for interesting effects. Here is a slideshow of increasingly large values. For the best conversion, error propagation is used to ensure colors are represented across the image. The default is 4. A smaller value tends to make the image too noisy. Larger values reduce the noise level. A value of 0 removes error propagation altogether. This slideshow displays the increasing error value, which is the inverse of the propagation strength, thus reducing the noise. The final option I want to cover is the composite gray hack. It turns out that the 2GS, certain RGB cards, and some emulators treat the two gray values as distinctly different, light and dark gray. This is annoying and doesn't match the NTSC composite color output. Here is the Virtual 2 emulator with the composite hack disabled. Notice the light and dark gray values ruining the image. And again, with the composite hack enabled, which is the default. The effect of the composite gray hack is significant on the hardware and emulators that differentiate between the grays. The effect is much smaller on physical CRTs and NTSC emulation, but not insignificant. Here is Applewin's TV out setting displaying an image that gets pimples in areas of smooth gradients like skin. By disabling the hack, those smooth gradients will look better. Yes, it is subtle, but for the highest quality conversion, and the output is known to be a CRT or NTSC emulation, disabling the composite gray hack gives the best fidelity. Hack enabled, hack disabled. Hack enabled, hack disabled. Special thanks to Rob Sheehan for his K2 presentation program, written in Plasma by the way, and all those who have supported Plasma over the years.
All right. Thanks, Dave, for an awesome presentation. So, do we have any questions from the audience?
We do. Actually, this two-parter. So I'm guessing we're pausing here, Dave, just in the middle to kind of catch the first half of questions, and then we'll play part 2, and then we'll go to the second.
Right.
Yep.
Great.
So I know this is a very compressed presentation. I did it beforehand just to make sure that I didn't lose internet because I have Starlink, which usually works, sometimes doesn't. But yeah, definitely very compressed.
I'm curious about what Dave called the saving to standard double high-res graphics format. I didn't know there is a standard. I know Beagle Brothers came up with a file save load method, and there were probably others.
Yeah, so it's just an ordering of the auxiliary memory and the main memory components of the double high-res graphics screen. Programs like Dazzle Draw, 816 Paint, all kind of defined the ordering of the bytes. So I just That's just kind of what we call a standard. What was the comment in Discord? Michael, I guess, also has a pointer to sort of the standard orientation of the bytes. You can kind of pick one of the two. I think everybody sort of decided to put the aux bytes first and the main bytes second. And that's just so you can import it into other programs like these paint programs and manipulate the image further.
Okay, thanks. Do we have another one? Yeah, Michael again is asking, how did you come up with the new algorithm?
So it took a long time. So if we go back to my initial comment about this is the spiritual precursor to my 2017 presentation on doing artifact colors, but using the Apple IIGS's super high-res graphic screen, which doesn't seem like it'd make any sense because that's usually an RGB only mode. But if you plug in an NTS monitor into your Apple IIGS, you can actually get these artifact colors out of it. And so that started a long history of trying to calculate the best way to convert RGB images, taking advantage of the NTSC color cycle. And we'll get into the gory, grimy details here shortly. But just like Mike was talking about in his A2C DVI, hooking up a scope to his output of his Apple IIc and looking at the bit stream that the Apple II spits out and thinking of that kind of in reverse. So instead of trying to generate an actual RGB image from the output of the Apple II, I was trying to think in reverse how to manipulate that bit stream the other direction. So that's kind of the conceptual thinking it took. Instead of using the more standard, just convert RGB image into sort of a simplified RGB model of the Apple II, it went down to the bit stream. And we'll get into the grimy details in part 2, which is a much longer part of the presentation. Hopefully nobody goes to sleep.
Well, Ron asked again, how big is your collection of double high-res graphics pictures and how many megabytes of classic cars and Star Trek chips does it
include? Too many is probably the right answer. Yeah, this has been a long process trying to figure out how to convert some of these images. So as we'll get into the next section, artificial colors or artificial images like cartoons or things with lots of solid colors don't actually convert all that well. No. Natural images, pictures, of people and nature seem to work well because it sort of relies on a noisier image. When you get something that's just a one flat color that doesn't convert super well, it actually ends up looking like our surround here, where you get combinations of colors that don't look as smooth as they would in a true RGB image.
Not a lot of fidelity, yeah.
So I have lots of pictures of old cars that tends to be my go-to source.
You'll have to publish them online at some point.
Yeah.
So Michael asked, do you process a single line or 2 or 3 lines, and how big is the local pixels for adjacent colors?
So interestingly, it's done a pixel at a time. We'll get this into the next part of the talk. I do propagate the differences, the error basically forward, so to the right and to the bottom, and so that's where you'll see some of what looks like dithering. It's just error propagation. I do no actual intentional dithering. So it's a very, very simple algorithm, and the next section will actually get into the horrible details of what this algorithm looks like, but it's incredibly simple, as I'll say about it right now.
Uh-oh. Eric asks, can you briefly describe some of the features of Pleiades?
No, it's going to take forever. No, so Pleiades is sort of the evolution of the plasma environment. And so what you saw me working there, and again, this will be sort of the follow-on part 2 of this. It's my command line interface. It runs on top of ProDOS. Everything that you saw was actually written in Plasma, and it's just as a programmer, as somebody who interacts with the computer at a low level, I like a command line interface. So Pleiades, what we saw there was just interacting with the Plasma code and ProDOS. With the command line, I added tools for doing file globbing, so you can use like a wildcard when selecting files. So that's how I was able to do the star.lz4 and get the whole list of files that were compressed and ending with .lz4.
Oh, okay. Interesting. Any other questions? I think we do not. So I think we'll go ahead and dig into the details then in part 2.
Okay, and then we'll talk about, this was actually making the slideshow part. So this was the part that if you wanted to just get some really cool results, you would import your pictures, and then you could turn your Apple IIe or Apple IIc into just a 40-year-old digital slideshow. So, this was really just, if you just wanted to make a slideshow using your own pictures, that was the point of part 1 here, without getting into those grimy details. So I don't know if anybody had any more questions about how to make their own slideshow. We'll have more time, I guess, after part 2, but try to stay awake.
Well, let's dive into the details then.
This presentation deals with the more technical aspects of the double high-res image conversion process. If you only want to make a slideshow, you have all the tools you need. If you want to know more about the conversion algorithm, the Plasma and Pleiades tools and build environment, then here we go. NTSC stands for the National Television Standards Committee that came up with the broadcast standard used in the US and a few other regions around the world. The old joke is that it stood for never the same color. It's not hard to understand why. The black and white video standard was developed with technology of the 1930s and cleverly expanded in the 1950s to add color in a backwards compatible fashion. The subject of this presentation is 70 years old. Then, in 1976 and 77, WAS designed the Apple II around the NTSC specification. It drives all the basic timing of the machine, to the chagrin of all you Apple II users in PAL regions. We will be skipping a majority of the theory and focus on color representation and how it interacts with the Apple II. In our case, the video luminance signal or brightness is simplified by the Apple II to an all or nothing proposition because it outputs video as a bit stream. The NTSC video signal uses a clever way to encode color using a low bandwidth method by implementing a color cycle to represent colors across the screen. Often described as the NTSC color wheel, colors can be represented by changing the amplitude of the video signal throughout this color cycle to sum up to a displayed color. Imagine rolling the color wheel across the screen, in the Apple II's case 140 times. Some simple examples would be a zero signal through the entire cycle would output black. A full signal for the entire cycle would output white. According to the NTSC specification, the 3 color components of red, green, and blue peak at the phase angles of 103.5 degrees, 240.7 degrees, and 347.1 degrees. A signal peaking at the beginning of the cycle would generate a bluish hue. I have not been able to find out why these values were chosen. Woz used his knowledge of how the NTSC decode circuitry in a TV would interpret the bit stream coming from the computer as colors if the bit stream was output faster than the color cycle. The example I use, for us old people, is the local weatherman would sometimes wear a vertically pinstripe sports jacket, I think purposefully to annoy the cameraman. If the weatherman was at the right distance from the camera, those vertical stripes would alias. The stripe width would be narrower than the color cycle and get interpreted as color. The weatherman's sport jacket would erupt in an explosion of color as he walked around. Woz ended up using a bit stream 4 times the frequency of the color cycle. And because it is a bit stream, the amplitude is either 0 or 1, full amplitude, leading to some pretty garish colors. Doing binary math, 4 bits provides 16 possible combinations to be interpreted as colors. It turns out 2 of the combinations, 0101 and 1010, get interpreted as gray by the NTSC decoder. This explains the 2 equivalent gray values unless you are using an Apple IIgs, RGB card, or one of the emulators that decides to differentiate these as light and dark gray, even though the NTS decoder does not. This is the reason for the composite gray color hack in the RGB converter. The Apple II's graphics modes give varying degrees of control over the video bit stream. The low-res graphics mode generates 16 colors by replicating the high or low nibble of the graphics screen 3.5 times per low-res pixel for a 40-pixel wide screen. Regular high-res graphics can only generate a subset of colors because it halves the bit stream rate, giving 280 horizontal pixels across the screen. You get 2 bits per color cycle, but the post Rev 0 Apple II could do a half pixel shift every byte for 6 high-res graphics color pixels with caveats. The Darth graphics, double high-res graphics mode, gives us control over all 560 horizontal pixels in the video bit stream, but boy does it make us work for it. Unfortunately, it took the 128K Rev B Apple IIe and later machines to support double high-res. A simple model of double high-res says there are 140 16-color horizontal pixels. The Apple IIgs, some RGB cards, and many emulators treat double high-res in this way. But in reality, NTSC color generation is much more subtle. The reason is that the NTSC color cycle isn't 140 independent cycles across the screen. It is actually a sliding window of color summation. Now we know how the bit stream is converted into a color image on the screen. Getting an RGB image represented faithfully using this model is more difficult. The traditional method has been to treat the double high-res screen as 140 independent 16-color pixels. This has the benefit of simplicity and using time-tested algorithms to convert high-color RGB to low-color RGB, doing a best attempt to match colors to a subset color space and dithering to spatially spread out the error. This method is capable of taking advantage of those display implementations that differentiate between light and dark gray, which can be quite useful, but to the detriment of an effectively lower output resolution. My algorithm, which I think is unique, calculates the RGB values of the NTSC subcycle pixels. A variety of values can be used for this calculation, but the default is to use the maximum RGB phase angles from the NTSC specification. The full horizontal resolution of 560 pixels is used to match the incoming RGB values, and by propagating the RGB differences forward, the best match should be found even if it is further into the color cycle than the current subcycle. The hard part to figuring out the algorithm was with the sliding window summed RGB value. I tried many variations looking at the preceding color cycle and scaling with different values to best match the RGB values, even looking forward to a possible future best match. But in the end, the simplest approach provided the best output. My final algorithm simply keeps a running sum of all matched NTSC RGB values scaled by 3/4. The incoming RGB pixel is compared to the previous summed and scaled NTSC output with and without the current NTSC RGB color subcycle. The best match is chosen and the difference is propagated forward. Because we are dealing with a bit stream, there is only one decision to make. Is it a 0 or a 1? By using the full horizontal resolution of the double high-res screen, diagonal lines can retain their full resolution and reduce the blocky look. Small details are retained, but colors may be lost or aliased. I will add that the results of the conversion look very good on monochrome screens as well. Colors are lost, but details are retained. Here is our test image of WAS using the Apple Win Color TV output. As we switch to the monochrome green screen output, look at the quality of the conversion. On a physical CRT, the results are quite impressive. The Apple Win emulator has the best color composite and TV output simulation I have found, but the new GS² emulator is showing promise. The new crop of HDMI devices for real Apple II hardware is very exciting. They are works in progress, but I hope they can get to Apple Win's level of fidelity. The advanced features of the converter provide for different phase angles used for calculating the NTSC RGB values. Surprisingly, the conversion differences are not that great. The options break down as follows. The default is to use theoretical NTSC phase angles. The ideal phase angles for 4-bit subdivisions of the color wheel, equal spacing of the phase angles at 120 degrees, and simple spacing, which uses 90 degrees between red and blue, then 135 degrees between red and green and blue and green. More advanced options of the converter include brightness, which adds a value to the incoming RGB pixel to lighten or darken the pixel before matching. Saturation adds a value to the calculated NTSC RGB value, perhaps not the most accurate way to adjust saturation. Tint is adjusted by adding a value to the initial angle to start the NTSC color wheel calculation. The default value is 22 degrees. This was determined empirically with many tests. I can't explain why 22 is the best value. Perhaps being half of 45 is a clue? Still not exactly sure. The internal state of the algorithm can be dumped to the screen before conversion takes place to ensure the values are correct. The NTSC RGB values are the most interesting to review. There is always room for improvement that can be made to the algorithm. I'm unsure how much these improvements would increase the fidelity of the conversion, but here they are. Using cosine to calculate the color wheel values may not be according to the specification. I wasn't able to find the definitive answer as to how the RGB values are to be calculated around the color wheel. Saturation adjustment is a janky implementation, probably not a valid method for image saturation. And matching solid colors isn't as good as I hoped. Error propagation and the color wheel calculations may contribute to the poor performance matching pure colors. The Apple Color logo required a lot of tweaking of parameters to get a close match. I would like it to reproduce such an image without so much adjustment. We'll now shift gears and check out the Pleiades environment running on an Apple II and the tools written using the Plasma Double High-Res Graphics Toolkit. Let's look at the Darth Graphics demo code that ran at the very beginning of the presentation, just to show you what the Double High-Res Graphics Toolkit allows you to do very simply. Here at the very top, we have our include files, which will bring in the different modules for the plasma environment, the Double High-Res Graphics Toolkit, and the sound sequencer. We then set the system flags to reserve the Double High-Res Graphics memory. Then into our actual code, where we define our variables for our string dimensions and the actual string itself that gets printed out at the end of the demo. Then all we simply do is read the font file. The Trade 54 is a very large font, and bring that into the graphics toolkit, calculate the extents of the string, which we'll use a little bit later, and it's all very simple, right? Then we set our Double High-Res Graphics mode, the color mode. Currently that's the only mode you can set. On the RGB card you can do a monocolor mode, but that's not enabled yet. And then we simply read in our converted Darth.DHGR image. Then we use the plasma sound sequencer to play our Imperial March converted from a MIDI sequence, and it will play until a key is pressed or it is complete. So all very simple to play that whole sequence there. The library will auto-detect a Mockingbird card and use that if found. Then we set our color and we print and draw our string centered on the screen based on the extents we calculated, and down just a little bit from the top. All pretty straightforward. And then we wait for a key press, and then return to text mode, and we're done. That's all it took to code up that simple demo. Conversion of the MIDI and the image is what took most of the time. I should mention that in the Pleiades command line environment, C will catalog files, P will set the current directory prefix, and slash will back you up a level of directory. So let's edit the Double High-Res Graphics Toolkit's test harness. This file has most of the API for the toolkit is exercised somewhere in this file. Much of the data is included in line as it was written before the tools to generate sprites and other images even existed. You will find the Double High-Res Graphics Toolkit sample code under the build/dhgr.tk directory. You will also find the necessary include files to build against the Double High-Res Graphics Toolkit in the inc directory underneath the toolkit directory. Let's navigate to the Double High-Res Graphics Toolkit's binary directory and see what we have there. Under the test directory, we can actually run that test harness that we looked at earlier. It starts off drawing full Double High-Res Graphics resolution lines. Then loads the WAS image and does a copy from one part of the screen to the other before showing us some compiled sprites, and then drawing some colored graphics lines. We get to see some text some sprites, some dithering, some more color dithering, even more color dithering. Now this is really just to show how to programmatically generate additional colors in the double high-res graphics mode. Let's navigate up and over to the demos directory. Here's the Darth Graphics program that we saw at the beginning of part 1, so we can run that from here as well. Now you've already seen how simple it was to create that demo. Now that we've checked out a couple of the double high-res graphics toolkits, test and demo programs, let's head back over to the build directory and let's bring up our double high-res graphics image converter. I don't think I've mentioned that I'm using the Pleiades text editor to bring up all of our source code and edit it here on the screen. And this is at an emulated 1 megahertz. Hope you can appreciate how fast the editor is in 80 column mode. Now at the top of the file we find all the constants for things such as the NTSC, phase angles for RGB, a bunch of data for the scanline order, and other variables used by the algorithm. Things don't really start to get interesting until we get a little bit further down and we see this routine called dist. This is what calculates the distance between the incoming RGB value and the color we want to match to. It uses 32-bit integer math because it has to square values. Now we've come to the routine that calculates the RGB values of the color cycle. Now it's using some fixed point math shenanigans to avoid switching to 32-bit math. The RGB value is saved off into an array that is referenced during the color match operation. And the RGB color match follows. This routine is the guts of the algorithm. It starts off by taking the previous red, green, and blue values and multiplying them by 3/4 to get 75% of the summed previous RGB values. These three variables are global variables, and here they are defined at the top of the file. There makes them just a little bit easier to reference. Head back to our routine to show that we then take the potential current RGB color match in the saved chroma array from above, and then calculate the distance between the incoming RGB color to the current NTSC RGB color and the distance between the incoming RGB color and the previous output NTSC colors. If the distance to the current is less than the distance to the previous, then the current RGB colors will be updated to be the previous RGB colors, and we will output a 1. The difference between the incoming RGB value and the output RGB value will be propagated to the following pixel and the pixel below. What follows are the initialization routines that fill in the gamma arrays for the different values of gamma, that read in the header for the portable network image format, read in the scan lines for each image, and then call the matching routine. So all that is just sort of the utility routines, and then at the bottom is where we see the output for the help message. Now that we've seen the source code and can edit it, let's move up a level and let's compile the converter with the Plasm compiler. We will output to a binary file called DHGR. I sped that compile up quite a bit, so we weren't just watching it slowly churn away. But now we can run the resulting Plasma module, and without any parameters, it will give us the help message. All this information and more can be found on the Plasma Pleiades GitHub webpage. At the bottom of the page, you will find links to documentation, YouTube videos, and disk images. Clicking on the Plasma language and compiler page will take us to the main Plasma tutorial and definition page. This was the original Plasma page. I've now moved down here just for the language description and tutorial. About everything you'd want to know about the language itself can be found here. Documentation for the libraries and low-level bytecode interpreter, as well as other source code, can be found in this link, which is really a link to the wiki pages on GitHub. As you can see on the right-hand column, there are links to almost all of the libraries with descriptions and API, tools and utilities that can be used from the command line. And here we're looking at the actual sprite editor for the double high-res graphics toolkit. Here is the page for the image converter itself, where we see all of the details for converting RGB images. Most of the information presented here is available on this page. So if you need to reference more detail, feel free to go to this page and check it all out. Lastly, there are links to videos. There is a Plasma video playlist on YouTube that contains a whole tutorial series on Plasma from the very beginning to the final double high-res graphics toolkit introduction. I won't claim it's the most exciting video series you'll ever watch, but it does cover quite a bit of information and can supplement what you find in this presentation pretty well. I hope you like this introduction to Plasma and Pleiades. Thanks for listening, and we'll start taking some questions.
All right. Thanks, Dave. All I can say is wow.
So I realized that was pretty dense as well.
A lot of complexity in there. So, well, we have a few questions here. So, without further ado, let's get started. Michael asked, Dart H, well, he didn't ask, it's more of a comment. Dart H graphics is such a pun and great test image too.
Yeah, well, it's because double high graphics memory map is literally insanity. We all know the high-res graphics screen is pretty complicated to figure out, and double high-res graphics kind of is brain melting. But it's what we were handed back in 1983. So I know there's going to be a follow-on question about how a beginner might want to start learning about double high-res graphics. And because it is such a crazy memory layout, I think the easiest way is actually to start with one of the multitude of libraries that are already out there. I think there's a few basic extensions that maybe Bugle Brothers, I think, has for double high-res graphics. Of course, I'm going to promote Plasma, but I don't know if any beginner wants to start with Plasma or not.
Oh, that's great. Yeah. Thanks, Waz. Right. He optimized it, and we have a wicked high-res and double high-res graphics memory map. So
yeah, but it save gates, right?
Save gates. Yep. Save chips. Exactly. Well, Ron asked, what got you interested in this topic?
Well, to be honest, graphics was my career, and started out with literally the Apple II, and I started with the Apple II Plus. So I never really spent much time with double high-res graphics until literally about 9 months ago, and I always knew that it was going to be a lot of work to really make it sing. So I put it off as long as I possibly could. and so I did spend time on the Apple II GS's, super high res NTSC artifact color output. And I thought, okay, I'll never have to go do that again. But then you start thinking, well, there is always double high res graphics that we haven't tried out yet. So Bill Buckles has done a pretty amazing tool years ago for doing image conversion, RGB image conversion for double high res. Plus, he did it for other modes as well. And I always thought, is there a different way to think about this process as instead of the more traditional, converting RGB to RGB, which was kind of the way, to do it, is to kind of go back to the bitstream concept and how it interacted with the NTSC video signal, and kind of go back to the core principle of how video is generated on the Apple II. So it was a deep dive, and it took quite a while. Daniel Henderson and I went back and forth quite a bit, comparing ideas, and he would send me over some artwork to play with, and so it was kind of nice to have somebody else to collaborate a little bit with.
Oh, very cool. So Andrew asked, and you talked about Bill Buckles.
Oh, Bill Buckles, yeah.
Yeah, way back in 2012, I found a Windows utility, Clipshop by Bill Buckles, to convert BMP to double high res. Did you get any input from him when you were creating your code or methods?
So no, I didn't. His is a great tool, and I think it really pushed forward the state of the art for image conversion at the time. And so I always kind of held that as sort of the gold standard. And if what I came up with couldn't improve upon what he had done, then I would say, next, and move on. I in fact used a lot of his images that he used in his experiments, and I feel that there some of the images work better with his algorithm. Some of them work better with mine. One of the things that my algorithm struggles with is, I think, artificial colors, like cartoonish, solid colors. I think Bill's algorithm does a much better job dealing with those kind of conversions. When it comes to like a natural image, a photograph, I think my algorithm actually does better than his.
Oh, that's interesting. You guys should combine and.
Well, Bill's been pretty quiet. I hope Bill's still around. I haven't seen him post anything in a while, but it'd be fun to get together and compare and contrast.
And compare and contrast. Yeah, that would be interesting.
See if there's a way forward to even combine some of the two algorithms.
Yeah, absolutely. So I think you touched on this one, but is there any more that you can really add to this? That was my question, is what do you think are the most important concepts for beginners trying to understand this?
First off, that it's kind of a crazy memory map. For a beginner, honestly, I think picking up one of the pre-existing toolkits, an AppleSoft Basic extension, just to play around with it, just to see what can be output. Because it's funny to go back to a computer that's 40 some odd years, 45 years old, and see if we can make it do new and unique things. Maybe that suggests we have too much time on our hands. I don't know, but I think there was a lot left on the table. Things moved so quickly. By the time DHGR came out, we were already looking at the IBM PC was coming out. The Apple II GS came out just a couple of years later. So it didn't, I think, get as much love as it could have if it was there from the beginning, perhaps.
Yeah, I prefer to call it pushing the envelope rather than too much time. Yeah. So, do we have another question? Yeah, from Ron again. What is your, and this is an interesting question, what is your original method for getting the images into your Apple II? I mean, there's no USB port where you can plug your camera in. So do you directly scan them in? Do you download them online?
Well,
Usenet, Ron's showing his age.
Well, that was probably one of the things holding us back in the day to getting images onto an Apple II to really play with them. I mean, I know I have some old Apple II literature. I think it came with the Apple II graphics tablet, and they had some digitized images. But back then, I mean, it was a chore to get some kind of a digitized image onto your Apple II. I mean, it was a big deal. Nowadays, it's fairly trivial, and I went through the process of using the GIMP as as my pre-processing. Now I know I think Chris Torrance may have written a front end to Bill Buckles' conversion program. Maybe Chris can jump in a while ago, and he sort of simplified the whole process where you just drop a JPEG or something, and it would do all the actual work of scaling it and getting it into the right aspect ratio, and then spitting it into an actual disk image. So I will say that I do have the C code versions of this converter. If somebody would be willing to take that and make a Windows or JavaScript or some kind of front end, I think that would go a long way to simplifying the process of taking something from your photo library and making it into a ingestible format into our real Apple IIs or our emulators. And that's what I use. I use an emulator. I used Apple Virtual 2 that you can share your directory structure as a ProDOS volume. So I would just literally copy the file, either the PNM file or the DHGR converted file over to a directory, fire up Virtual 2, and be able to manipulate it inside Virtual 2 directly. Now, Virtual 2, as I sort of demonstrated, doesn't do the best job of NTSC emulation. So I have an intermediate disk image that I share between Virtual 2 and AppleWin. So I run AppleWin on my Mac by way of Wine that allows you to run Windows applications. And Wine does an amazing job of running AppleWin. AppleWin, it must be very, very good about not doing anything esoteric with the Windows system. So it runs great under Wine. And so that was how I did a lot of my first pass tests to make sure things were going the way I wanted. And then I convert that disk image onto a USB stick, and I pop that into my CFFA 3000 onto my actual Apple IIe that has a composite monitor, Apple Color monitor on it for final testing to see that it indeed did, looks as good as possible. And that's the challenge with emulators and even our new DVI hardware is to emulate those subtleties of composite TV out. It's all analog, and we now live in everything full digital, so it's hard to match some of that analog warmth as the old school audiophiles will say.
Exactly. Well, thank you. I think we're out of questions and we're out of time. So
Okay.
Thank you so much. And if anybody wants ask any more questions of Dave, go over into the Discord channel and
I'll hang out there for a bit.
Yep. And he'll hang out for a bit.